Okay? So let's start with the compiler optimizations. Sorry, with the compiler. Then we will see the optimizations. So essentially, well, yes. So essentially, we talk about this part here. Okay, so the Cray compiler, the GNU compiler, and then yes, in this case, it's just Intel compiler. Okay. So again, when you are compiling for Daint, you need to use the wrappers. So it depends if you are running in C, C++, or Fortran. And then it's essentially replacing when you are using, for example, G++ or all the other commands. And then you can use the standard options and the file you want to compile, right? Depending, these wrappers will use the real compilers, depending which program environment you have, right? So it's Cray, GNU, or Intel, and then, of course, you can do swap. So just make sure that you're using the right compiler, right? So you need to be sure that you have this module here. This module, Cray PSND bridge, is by default, so you should have on your system. And this module will add some other, for example, options. Let's say they will add for AVX vectorization because it's available on Sandy bridge, okay? So you need to have load this module. And then, of course, you need to use APRun to run in parallel for the compute nodes. Something we need to understand is that by default, the linking on the system is static, okay? Which means that this is some kind of legacy, okay? Maybe it will change in the future. The meaning that we are making a fat executable where you are putting all your links to the libraries, okay? So if you want to change, depending if you are doing something, this does not depend on the compiler. Whatever you are using, Intel, Cray, GNU, you will start, by default, you will do static linking. If you want to change the behavior, the way is you can pass minus static or minus dynamic. Minus static, again, is the default, or minus dynamic to the wrappers. Otherwise, you can set this environment variable. Suppose you don't want to change your make file, right? Adding these variables. You can set this environment variable, for example, export this Cray P link type dynamic, and then you will do in dynamic way. So sometimes you have cases, for example, where you want to link to dynamic libraries. You don't have static version of those libraries. It can happen with Intel, for example. So you want to set this variable here, okay? For GPU, since we are linking to CUDA libraries, which are just dynamic libraries, okay, .so, so we need to use dynamic. Indeed, when you are loading the module for the GPU, dynamic is set by default. Automatically, if you do module show, Cray, P, accelerator, whatever is there, NVIDIA, blah, 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 you will see that it's setting this variable by default for you, okay? So just to give you an idea, static means that you have fat executables. So basically, you compile with a given environment, let's say with a GNU environment, and then you can run in another system because we are putting everything there inside the executable. And even if you have another program environment, it doesn't care because essentially you are compiling, when you are compiling, you're putting everything there. So then this, I think, is one of the reasons why static can be better, right? Then there are other possibilities. Here there are ideas why maybe static would be better. Otherwise, it's dynamic. For example, you have a smaller executable. Then, of course, you have dynamic linking at runtime. So you will load the libraries. So you can piece it over just because you are loading dynamic libraries. And, of course, the libraries should be there, OK? So when you are compiling, there is a library. Then you move your executable to another system. And the library is not there anymore. It will tell you that it cannot find the symbols, right? So this is one of the problems why maybe dynamic is not good, okay? But sometimes, for example, for tools or CUDA and so on, you are forced to use dynamic, okay? So there are three ways, basically, that you can use for linking in your application. So the default one is, again, is the static. Then you can apply this kind of pseudo-static. What does it mean? You are doing dynamic linking, but then you have set this variable here. And essentially, setting this variable, it will tell during the linking to link also the path to your library, essentially. So when you are running again, you don't need to set, you remember, when you are doing dynamic linking, you need to inform when you are running the application, where are your libraries, right? So you are using LED library path. There is this environment variable to set. If you don't want to set this LED library path to inform where is your library, you can use this Cray IDR path. Essentially, we'll put minus WL minus R and put the path when it's linking. So it will do automatically for you setting this variable. And then, of course, this last case, dynamic module, when everything is dynamic, right? Even the paths are dynamic. So you need to set your export LED library path, okay? And you can do export LED library path to Cray LED library path, and this guy here is coming from the modules, okay? So when you are compiling, loading the right modules, you will set this variable here, and then just doing this, you will run and you will get the right path to the libraries, okay? So by default, we'll use this guy here. Otherwise, you can use these other two. Okay, now let's move to the compiler. So this was already shown yesterday. It's just to give an idea of the Cray compiler environment. So CCE, I will call from here CCE, okay? So CCE has a lot of default optimizations, like vectorization, the possibility to do parallelization. By default, OpenP is there, okay? You can have other possibilities to control inlining, to control other optimization, loop unrolling, and so on. So at the moment, we are supporting essentially all the Fortran standard, okay? We are not supporting C++ 2011. It will come on the next release. OpenP 3.1, but guys are working on OpenP 4. And the OpenACC 2.0 was the first compiler to support OpenACC, sorry, 2, okay, 2.0, okay? So OpenP, as I said, is owned by default. So this is completely different from the other compilers where you need to put your flag, right? -f OpenP or -OpenP, depends if you are using GNU or Intel. Here is by default. So sometimes maybe you are using a makefile for the CCE, where of course you are not setting this flag because it's owned by default. Then you want to try with GNU, and of course then you need to add the flag. Otherwise, you will not get the same performance just because OpenP will be off unless you set the flag. So we are supporting Sandy Bridge, Ivy Bridge, depends, again, you have this module, Cray P, Sandy Bridge. Of course, if you're running on an Ivy Bridge, there is also the module for Ivy Bridge. We are using also NVIDIA, so the CUDA. We are supporting MPI 2.2. Again, also in this case, there are more or less all support for MPI 3 functions. The Pegasus languages, so I will skip this part here. Then it's supporting hybrid, MPI plus OpenP, support for IEEE floating point arithmetics. Then all tools, there are special options that you can use when you are compiling with CCE for the tools. We will see tomorrow, these tools for profiling. Then something called a program library. We'll describe later. There is also a possibility to use with other tools, Reveal, which is a tool by Cray. And the current release that you can find on your system is 8.2. I guess it's 8.2.4, something like this on Daint. You can just load your module for Cray. It's by default, by the way. So you can see what is the version there, which is available from September last year, okay? so I made this example. Now it's not easy. So this is just an example. Some sequential portion, and this sequential portion is running on the front-end node. Okay, so back to inlining. So when you are doing inlining, you have several files to compile. The inlining by default is done inside a single file. So let's say you have some Fortran modules where you have several functions. By default, the inlining will be inside a single file, right? So when you are compiling a single file, you will understand, okay, some of those functions can be inlined. But now, suppose you want to do cross-inlining, so between different files. So let's say you have a module, you are including this module, and you want to do inlining from another file, okay? What is called interprocedural optimization, IPO, okay? So this will come with this option here. So you are saying, okay, I want to do inlining, and I want to use the inlining from another file. So this, again, Fortran option, C++ option. And so this is just an example. So I want to do inlining, instead to do for a single file, this is the case for a single file, I want to do, or more files, right? I want to do for an entire directory, all the files inside a directory, okay? So when then you are compiling a given file, you will understand, okay, those functions are coming from a different file, I will do the inlining for you, okay? Does that make sense? Questions? Anytime if you have questions, something to ask, okay? Of course, cross-language inlining is not supported just because, you know, between Fortran and C there are some differences in the objects. So it's not trivial to do this kind of inlining. But otherwise, you can do inlining. So you can specify to do inlining for your entire program. Maybe, of course, there is an option for that, instead to put all files here or your entire directories. So you can do this kind of stuff. So in this case, it will produce for you a program library. So you set -HPL, you set a given path, and it will produce inside this path, which is a directory, will produce a lot of files. Then you can go to see inside these files. It's not easy to understand what it's really doing, okay? It's a kind of meta language. But what is interesting from here is that you compile once, it will produce this library. And you are storing all information during the compilation. This information are useful then to recompile your program to apply optimizations. So the next step, you will compile using this HWP option, okay? So you are compiling twice. The first time, you are producing the library. The second time, you will recompile using the information from the library, okay? So the second step will try to optimize. It will try to optimize since you know all the information from the program, okay? So suppose I have file A with a given function, is inlining a function, let's say, foo, okay? And this function foo is in a second file, okay? If I do by default, foo will be not inlined, because foo is another file. If I do option, foo, you will understand, okay, it's coming from this other file. Okay, so I know where is this function, and I will do the inlining. So doing this kind of option, you can do better optimization. By the way, these options are also for the other compiler I will show you later, okay? The thing is, when you are doing this option, maybe the program will, will be really, really slow to compile because it's trying to do all this kind of cross-reference between files and so on. Maybe it will take a lot of time. So there are also ways, and all these kind of optimization are done at linking time. So it's going to be very, very slow. GNU, it's impossible to run, actually. So there is an option in GNU, which is -LTO, okay? So you can do your entire program. Of course, when you are doing this kind of optimization, again, you can set how many processes you want to do, because you can do also in parallel, okay? Now it's not like make -J, because make -J, so how many processes you are doing for your compilation, it will do several lines of compilation. Here we are doing a single line of compilation, but this line of compilation will be very long because he has to understand all possible other files where to do inlining, okay? So maybe you want to do inside a single line parallelization, okay, for easy, fast compilation. And there is a way also to set this mproc and to tell how many processes I want for compiling, so to speed up compiling. So again, when you are using this option, of course, these other two are not, this guy here is not useful anymore, just because I don't need to specify any file. It will just inlining for all files, okay? And of course, still, you can control the inlining by those options. So again, 3 is the default, but you can set less or more if you want to be more aggressive in inlining. So just to clarify, why we want to have inlining. In the next presentation, I will describe why we want to have inlining. So there are cases, for example, for vectorization. If you have a loop, and inside the loop, you have a call to a function, and this function is not inlined, essentially, when you go to the line, to the function, you will call the function, put all the variables in the stack, and you will destroy any kind of vectorization. So it's clear that if you want to get vectorization loop, you need to inline all functions, for example. If you want to move to a GPU and you are not doing inlining, cannot be possible. There is no possibility. I mean, still you can call the GPU, but the performance are very, very low. Okay. If you are same for OpenSCC, so inlining is very important if you want to get some specific optimizations like vectorization. Okay. This will be part of. So this is just to stress that the compiler is very aggressive in this kind of vectorization, this kind of inlining. Unrolling. Unrolling is a technique that I will show in the next presentation again. It's a technique that you can use to get performance from a loop. And there are options also for that. So this is by default, it will try to do any kind of rolling. But sometimes maybe you want to avoid because maybe you are already doing a rolling. So you are doing a rolling by hand. So you don't want to leave the compiler to do a rolling over a rolling, I would say. So maybe you want to switch off the rolling sometimes, okay? Now, again, same option for vectorization, also in this case. So the compiler will understand that some loops can be vectorized, okay? And there are flags that you can use, again, for Fortran and C++. So 2 is the default level. You can be even more aggressive. Doesn't mean that then the compiler will do better vectorization, okay? There is a way then to understand which loops are vectorized or not, okay? So we can have some output on the screen while it's compiling and just to understand what is compiling or not, okay? Right. Now, another interesting point is floating point optimizations, okay? So again, CCE is very aggressive in floating point optimizations. There are several levels of floating point optimization. So 0, this is the option, same for Fortran and C++. 0 and 1 are the low level, let's say. You are basically not doing optimization, so you are strict to the standard, the IEEE standard, okay? So don't expect, for example, this is good if your code is, you need to be very precise in some calculation and so on. The default value is 2, so we are already aggressive, okay? If you are using Intel compiler, it seems that a lot of people are using Intel compiler. Intel compiler is using this option FP-model, and by default it's fast1. Essentially, it's slightly less than n equal 2, okay, if you want to be. But then we have other two options. Intel compiler is fast1, fast2. We have other two options. There are other options for doing, you know, subnormals and all this other stuff. Then in a Cray compiler, we have other two options, 3 and 4. 3 is what we suggest. Most of the code can run with 3 and get a lot better performance, and you are not, you know, having problems with precision in your calculation. If you want, there is also 4, but I think we suggest don't use 4 unless you want to have sometimes wrong numbers, wrong results, just because rounding it will be large. But maybe you want to use 4 just to check your application. So if you have some results between 4 and 3, maybe it looks like that 3 then is working well. It's just to prove that 3 is working. So you will be more aggressive just for checking. Okay? This is a table that you can get again in the main page, where you see all the kind of optimization, for example, for divisions, exponential, all this kind of stuff. Depending where you do from here to here, the more aggressive, you will see that then it's changing basically everything. So let's say safety from maximum, which is the best, I, which are in the middle, then this is very low. So here you can get to whatever, okay? So let's say you have a convergence algorithm, then of course, maybe your program will run forever just because it's not able to reach the convergence, okay? Now, this is the case. Suppose I run with different compilers. So in principle, the standard deviation is the same. The both compilers should apply kind of optimization to get the same result. Of course, it's impossible, because if you're running different compilers, they will produce different code. Even inside the same compiler, if you have different versions, they will produce different results, okay? So try to have results similar between two compilers. It's more or less impossible. Unless your algorithm is making 2 plus 2, then it's trivial, okay? But if you have some kind of complex algorithm, it's not easy to get same results over the same compiler, different versions, and between different compilers. But of course, you can set FP0 or 1, okay? For example, if you want to have the same results between GNU and CCE. And then there are other options you can apply. For example, for parentheses, okay, the compiler will apply for you parentheses, try to reduce the approximations and so on. So all these rules are just to avoid, just to reproduce your results. So to be more similar to the standards, try to reproduce your results between different compilers, basically. There is also a possibility when you are running parallel, right? You know that if you are doing a reduce in OpenP, in principle, depending how you sum your elements, right, you can change your result. So if there's parallel, you can force to have all the same reduction over the time, always in the same order. And there is a flag for that. And this flag you can set, okay, do all the time, everything at the same way, okay? Or we can do to tolerant. Here you have less performance, okay? Here you have, best performance, but of course then maybe you are losing precision, okay? So suppose I want to run twice the same code, I want to get the same result, maybe I want to stay with this or this guy here. This conservative and default, right? But if I want to have the best performance, again, I made the example for the reduction where you want to sum numbers. I want to sum those numbers in the same order all the time. So maybe I want to change this option. This is specific for parallelization, okay? Then we move to other options. For processing, these are for Fortran. So when you are running you are compiling with the Fortran compiler, depends on your extension, you will understand which kind of Fortran you're using. Fortran 90, 95, and so on and so on. Okay, so the extension should be like this. You know that the standard Fortran is, you need to have 8 spaces at the beginning and so on and so on. So there is not extended form, right? Otherwise, you can specify those flags, and those flags are able to basically, you will understand everything like not from the extension, essentially, just looking at Fortran 90, basically. Okay, so EP and these other two options, basically. EP will just not compile. It will just do preprocessing of your file, and this guy will also compile. So sometimes maybe you have wrong extension. Okay, you are not in those cases. Some people, they put FTN, small FTN, or some other options. So maybe you want to set also this guy here just to have the processing of your files. Other options, this is specific for C++, is the restrict option for the pointers, okay? So you can have also this option for the Cray compiler. Cache optimization, again, in this case, you can set, so this is useful for prefetching, so optimizing on the cache. It doesn't mean that if you change this value to 3, it will be better. So usually the default is good enough, okay? So the default is 2. Then flags for diagnostic. So I would say sometimes you want to understand which are the optimization you are using. So you can set these 2 flags here, depending Fortran or CC++. It will show you which kind of optimization you are doing specifically, okay? Because when you set -2, -3, it means these are just different other optimizations. So you want to see which kind of optimization you are doing. And most of these optimizations maybe are coming from the program environment, just because you are doing module load Sandy Bridge, okay? So you want to see, these other options are for check bounds, okay? So sometimes maybe you get some violation, memory violation segmented because you are reading some elements over the bound of your array, and maybe you want to have an interruption or exception when you are doing this. You can set this guy here. It will just add some checking code. It will you are doing in this situation here. This will just not compile. It will just show you what you are doing. And this option is, I would say, quite interesting because it will just set initialize to 0 all the variables you are declaring, okay? This is just because sometimes you don't initialize your variable, so you will get random values. Maybe sometimes you are using these random values. So unless you remember to initialize. So of course, the compiler will tell you a warning, but most people, they don't see the warnings. They just ignore. So you can get some problems there, okay? So you can set this guy here, and of course, then there's in performance because maybe you want to have a different value. So first you initialize to 0 and then to a different value, okay? So this is just the recommendation. So most of the code can run with this option, -all3 fp3, which is a similar, this is just short way to write in this way, which means that you are doing a quite aggressive optimization, standard optimization, and then also optimization for floating point, okay? If you get problem here, you can have -all2, and of course, if you have numerical problems, you can get to less, so a ft2, okay, which is the default. Again, if your program is seriously, you want to do comparison with different compilers, or you want to, get the same result because you are really sensitive to results, to numbers, maybe you want to use FP1 or FP0. Again, not to use FP4 because maybe it's too aggressive just for checking, okay? OpenP is on by default, so you don't need to set any flag for that, like the other compilers. And also auto-training. Auto-training is off by default. Then you can use this flag here, and it will enable auto-training. So the compiler will say, okay, this loop can be parallelized using OpenP. It will add for you directives. It will parallelize with OpenP. If you don't want to use OpenP, and this can be the case, for example, I just want to have a serial application. So just to make sure that I don't want to use OpenP, then you need to specify. And there is flag, right, which is -h, no OpenP, or you can use these other flags here. Just make sure that you are not using OpenP. Questions so far? There are options that you can. Most of those options. Work that we can do in a Cray compile with a single flag. Sì, perché l'abbiamo sostituito ieri. Scusami, mi sono anche dimenticato di dirlo. Che è successo? So, do you have questions? 2 minutes break. Curiosity. Can I do this with another compiler? I can tell you what are the other options. But I have some slides at the end. So. Yeah, it's easier, easier.
So you've got that example.
Sure, sure, sure.
That's most common use.
Yes, yes. So if you are using Fortran, this is just for Fortran, and you are using streams, right? So you are dumping to, let's say, to the screen or to a file. The compiler, when you are doing, sorry, the compiler will try to use, you know, depends if you are dumping numbers and so on. There are some format that you can use, right? So for example, in the Cray compiler, by default, if you are printing an array, let's say this is an array of 4 elements, right? And I'm just setting to these 4 elements those values. So it is the same value to the 4 elements. And then I do print. The Fortran will tell me, okay, this array contains 4 elements with this value. And this is 4 elements with this value. This is the default for the Cray compiler. Okay? If you do in another compiler, you will see the output like this, for example, Intel. Okay? So this is just a short way to dump the information. Okay? So I don't want to change my program. Okay? So I just want to compile with the Cray compiler, but I want to have the same output just because maybe I do diff between the output, between different compilers. Okay, so with diff within files, I will see this difference. So without changing the program, you can use those commands here. So this is just an example. Okay, there are these examples to something else, and this assign command is available for the program environment Cray. Okay, so what you will do, you will set export. You will set a given file, temporary file. This temporary file will be declared in your directory where you are running, and then you set this command here. Those options are explained when you do the main page, okay? And with this command here, you will say, okay, please need the information not in this format, but in the long format. So this is one of the difference between Cray when you are dumping Fortran results, and of course, again, as Alistair was saying, instead of 4 elements, we have 1 million elements. Maybe it's better to have the short, because otherwise you will dump 1 million elements on the screen, same element, maybe it's not really useful, okay?
Some code will write out data and then read it back in.
Yes.
Complicated reading. And they find that, you know, because it's written in text, this kills
Any, yeah.
most other compilers.
Yeah, that's another point, yeah.
But it's a feature.
Yeah. So you can have this kind of flags, and without touching your code, you can easily change with this command here. Again, this command is just available for Cray program environment. Okay. Then we have a full set of directives. Okay, so you can control low level, let's say in your directory, in your program, adding directives. These are the directives for Fortran. Again, of course, we have pragmas for C and C++. There is also this keyword, because some of these pragmas are similar to other compilers. For example, IVDEP is also for the Intel compiler. Okay, so maybe I just use for the Cray and not for Intel. In the C, C++, I just need to add this guy here. Okay, this is just to avoid that the same pragma will be used for another compiler. Maybe you want to have a pragma just for Cray compiler. Okay, so these are a set that then you can do man directives or man loop info to see what are these pragmas that you can add. We will see later in the next presentation, for example, cases where you want to add some pragmas just to inform the compiler that you want to apply given optimization to specific loops. Okay? So these are the macros. So suppose there are pieces of code that you want to just use for a given version of the compiler. So these 2 macros are declared by the Cray compiler by default. It's the same for GNU. Underscore GNU, and then you can have the version, or Intel underscore Intel. It's always the same. So you can have something like this again, but otherwise you can use this keyword here, and you need to specify like this, okay? Okay, now, this is the second part of the presentation. It's quite interesting. Now, we understood, okay, we have all these full set of options. We can play with them. So we can set, okay, different compiler options. So we can see the performance. We can see the result. We can make comparison with other compilers, all these funny things, okay? Now I want to understand what the compiler is doing, which kind of optimization is applying to loops and so on, okay? Just to see, okay, well, this loop was supposed to vectorize with GNU. Now it's not vectorizing with CC. So why? Okay. Again, the other compilers will tell you on the screen, you can have some level of verbosity, which kind of optimization is applying. Okay. With the CC, there is a better way to do that. Essentially, we'll dump you the information in a file, and then you can look at the file. So you will use this option here. When you set -rm, it will produce a file. The file is the name of your file you are compiling, right? Plus LST. So we'll do this. This is part of the and so on. So you will see this is the legend, right? So you have different letters, and with these letters, it has different meanings. And then let's say you have a piece of code. It can be Fortran, it can be C, it can be whatever you want. And you see here, for this, it's a large loop. There are 3 loops, right? There is another loop. And you can see here which kind of optimization is applying. Okay, let's say, what does mean B? B means blockable, here, blocked. So it's applying kind of blocking, okay? Then you see here vectorization, okay? And here V is vectorization, and so on. So in this way, I can really see what the compiler is doing, okay? Which kind of optimization is applying in the code, okay? No other compiler will provide you the same feedback, okay? So for each file you are compiling, essentially you then go to, okay, again. Then you do profiling and see, okay, this function was taking 5 seconds in GNU, and it's taking 1 hour in CC. Why? You dump this information. You just compile the file with the flag. You dump this information and say, oh, here, come on, it's not vectorizing. Why? And then you need to investigate. Usually it's the other way around, okay? But it can be also the GNU is faster sometimes, or Intel, okay? So you will dump this information for each file, and you will get also, at the end, you will get also informations, okay? So these are kind of messages that you can get also on the screen. All these messages will be also on this file. Essentially, you have this information, and you will see also, these are messages that you can use. For example, here was unrolled 4 times, 31, this loop here, okay? And you will get this kind of information. So you really see what the compiler is doing, which kind of optimization is applying in your file. Compiler messages. When you are compiling, you get an error, and you want to understand what the error means, okay? So let's say this is the error. You are just compiling here. I'm just doing this kind of it cannot be, because 8 is not part of octal. So what I do is there's this command here, explain. I put the error. It will tell me something more about this error. Again, explain is part of the Cray compiler, okay? So you need to load this program environment to get this command here. So you can get hints on the error, essentially. Sometimes some of the compilers, they will tell you, this is the error. It's kind of obscure. You really don't understand what is the error, okay? People claim that LLVM is now solving this problem, because there is actually they also introduced the colors, okay? Because sometimes most of the errors are really impossible to understand. And GNU, sometimes it tells you this is an error in an empty line. And you see, oh, wow. Okay, so with this guy, you will see some useful messages for the kind of error you have, okay? You can control the level of verbosity of your messages. So you can switch off any kind of message, or this is by default, of course, you will get a message. So these are the warnings, basically, you have on the screen, right? And then there are several levels. So let's say, by default, warning will go, okay? If an error, will stop. But you can have, suppose I don't want to compile if there is a warning, you can have this setting this value to 2, and will stop when I have a warning. So you're trying to compile, there is a warning, it will not compile, it will just stop, okay? So you can easily, without compiling with warnings, you can easily, and then of course you have citation, note, and of course comment, so you can stop to, so you want to really see what the compiler is doing, you don't want to compile your code essentially, you want to just try to avoid any kind of messages from the compiler, okay? Okay. So this is just to control. Sometimes you want to really, okay, I'm interested in the warnings. I just want to avoid any kind of warnings, okay? So I just want to see all the warnings and try to figure out why there is this warning, how can avoid it. Okay. Questions for all people? Are you ready using Cray compiler? Okay, good. Question, yes. Mm-hmm. Cray. Yes. All the initial part is Cray. Then we will move to some of the commands that you can get with GNU and Intel, okay? So it's kind of comparison. Explain is, of course, not. Intel doesn't have any. Usually what you do when you get an error with Intel is go in Google, put the error message. That's the way to solve. But Intel is doing some good job. GNU is sometimes it's really impossible to understand which kind of error you have. Okay, so comparison with the other compilers. I said, with the GNU, the default is -1. So really don't do any kind of optimization, essentially. Just doing few optimizations. With the other compilers you have, with Intel, the default is -2. It also includes vectorization. With GNU, you need to specify vectorization. Otherwise, it will not do any kind of vectorization, any kind of lining. So by default, GNU is doing nothing, okay? But usually, since it's available from Linux, it's there, so you will try it sometimes in your life. Intel, you need to have a license for that, which is quite expensive. So maybe you're just, using. And these are most of, let's say, vectorizations include some loop transformations, so some way of inlining and so on. CCE is even more aggressive, so we will use -2. Again, -2 for CCE is slightly more than -2 from Intel. And then we will have inlining by default, vectorization by default, aggressive floating point optimizations, and so on. So CCE is more oriented to performance, so you will have even better by default, okay? Flags. Yes. All right, so to get feedback from the compiler, I mentioned, there you can use -rm. It will dump you a file where you can see all the loops, all the kind of optimization, and so on. There are also ways to do with Intel. Actually, with Intel, it was introduced with the version 13, so it's 1 year old. With GNU, it was introduced with the last version, 4.8, okay, which is even younger. So you can set, this is dumping on the screen, okay? -opt report 3, it will tell you on the screen. Otherwise, you can dump in a file which kind of optimization you are doing, basically, which kind of optimization the compiler is doing. There is same option for GNU. As I said, this is something new option. So I never tried it, so it would be interesting maybe to take a look. I don't know which kind of messages it can tell you, but you can also dump this information on the file. Again, I found that the GNU, sometimes it tell you, I cannot vectorize because there is a dependencies. Then it's really not useful because you cannot see the code. With the Cray compiler, you will see that you have code on the left, code on the right, optimization on the left. With the GNU, you will get these kind of messages. So then you need to open your code, go to the line, and see what it's doing. Okay? So I really found that Cray is doing a really good job. Yeah. But this is something new. This is in version 14, which is available now since 2 months ago. Okay.
People want to see vectorization information. It's still not as good as ours.
Yeah. The Intel philosophy is I will do everything for you, okay? But again, most of the time maybe you want to do something, and so you want to see what the compiler is doing for you, and then try to do better maybe. So options, -x when you're loading the Sandy Bridge module, this is added by default. You can do module show Sandy Bridge, Cray P-Sandy Bridge. It will tell you that it's adding this flag by default. So this kind of vectorization, you have registers, let's say, for vectorization for SIMD instructions that you have on the Sandy Bridge. The level optimization, again, is -2 for the Intel compiler. You can try -3. You will do better. Don't expect, also in this case, better optimizations. It's just, I use a -3 most of the time just for checking again. So I will use -3. Sometimes with the -3 is not working, then it means that maybe there is a bug in my program, okay? So I need to fix it. But production code, I will use -2. If you are brave, then you can use -fast. which means that you are doing any kind of dirty things for numerical stuff and so on. For setting floating point operation, you have this minus FP model. So by default, it's equal 1. You can use equal 2. You can have better floating point optimizations. But then you need to add other options, for example, to get the precision. So here we'll do the reciprocal, or you will do also precision for square root. Okay? These two options basically are included when you're doing the Cray compiler when you are doing FP3. Okay? Here, even if you set 2, these are not included. Okay? Actually, Intel is able to set the precision for some functions like cosine, logarithms, and so on. There are also flags for that. Okay? But you need to add these other flags. So sometimes it can be, well, not. You need to understand those flags, by the way. So loop unrolling, these are the options that you can use in Intel. Okay? So basically, here there is no way to control the unrolling. There are flags for that, but you're just setting, okay, I want to have a rolling for a given loop, or want to have aggressive unrolling, and most of the time aggressive unrolling doesn't work. It's just give you the same performance, same result. With the GNU, again, you can set here the flag for AVX. Again, this is set by this module, okay? But you can also specify if you want, just to make sure that you are doing AVX. So -1 is the default, but then maybe it's better to use -3. There it's not, I mean, it's working well for GNU, -3. And then again, you can use -fast if you want to get the best from there. For the math, you can use -f fast math, which is not included by default. So sometimes people, they try to compile with the GNU default options and Intel default options. Forget about Cray, which is much, much faster. And of course, Intel is faster. Intel is faster because they use -2 by default and fast by default. GNU is using -1, so no inlining, no vectorization. It is not using fast. So to be fair between the two, you should at least put -3 on GNU, -f fast math to be similar to Intel compiler default. Okay. And then of course you have also here flags for unrolling of the loops. Okay, this is just to give an idea between the three compilers. The most useful options. Again, these are what we basically suggest. Okay, so you can have this aggressive optimization, otherwise you can get I mentioned before the library. So this is something that you want to use for inlining for your entire program. There is a flag that you can use for Intel. If you use this flag for Intel, it will do this kind of inlining during the linking. There is no way to do in parallel, and essentially you will get a lot of information and it will run forever. Again, for GNU compiler, even worse. I mean, I found that some specific code you will compile with this option maybe for hours instead of minutes. So, okay. With the Cray, again, you will dump first we will dump the program library, then you will recompile using the information for the program library. Okay? There is a way to use MKL, which is the math library, kernel library from Intel in GNU. Okay? And with the Cray, we have our specific library, will be on the last day, libc. So essentially, you need to load the module for Intel. Then you do module show. Okay? And using module show, you will see what is the library. Where is the library? Where is the path to the library? Okay? You will see that it is this Intel underscore path. Okay? Then you go in your Mac file and use this path here. You change the program environment to GNU, for example. Okay? And then we can use MKL in your program. GNU. So you can use MKL from Intel in your GNU program. Program compiled with GNU. Again, you need to set to see what is the library. Of course, when you do a load of the module, moving from Intel to another, let's say, GNU or Cray, of course, this path will be not available anymore, right? So you need to figure out what is the path to use it. That's it. These are the main pages. For the compilers, of course, we have also main page for developers. You can try it. Okay, depending which program environment you are loading, then you need to use those commands here, and you will get all the information. Sometimes maybe instead to do module, yes, there was this problem. So you can load your program environment. Say program environment is Cray. And then you will see that it's loading also the Cray compiler. Okay? But then that means that you can do module load Intel. Module load Intel will load the Intel compiler. So now you are in a situation where you have the program environment from Cray, you have the compiler from Cray, and then you have another compiler from Intel, right? Since we are loading, the wrappers will use the Cray compiler, but now I want to use, for some reason, so you have an environment where you have Intel and Cray. Maybe the two will conflict. Just to make sure if the wrapper is linking to Cray or Intel, you can do this. So just to make sure, okay? You do, let's say, CC minus V. If it works, means that it's coming from CC or Intel. And then it will tell you the version. Of course, if it's CC, it will tell you the version from CC. If it's Intel, it will tell you the version from Intel. Now we are sure that the wrappers is linking to this compiler. If it doesn't work, it means that it's coming from GNU. And then you need to use minus version. This is just to make sure that I'm using the right version of the compiler. Okay? The wrappers are using the right version of the compiler. Okay? And then there are also documents that you can use to get more information on the compilers for Cray. Summary. So all the three compilers are available. You need to play with the flags just to see what is the set of flags that are best for you. Usually you look in the performance, but then of course you need to look also in numerical precisions. So just to see if you are able to reproduce your results. Clearly there is, it's not easy to find the best compiler, okay? It depends your code. Some compiler can do some kind of optimization out of the box. Some others can do other kind of optimization. So sometimes you need to change your code, which is the best solution, or otherwise you can teach, let's say to the compiler which kind of optimization you want to do, which kind of flags, try to add directives and so on. This will be for the next lecture, okay? So you need to try to convince the compiler to do some kind of optimization, okay? So if you find a situation where the GNU or Intel is faster than Cray, just to let know, CCE, just to let us know, and we'll see why, okay? So for the next release, we will try to introduce these new options, new optimization and so on. Questions?
So you mentioned that the sandy bridge module is activating any optimization.
No, just AVX.
Not just AVX.
So if you do module show Cray P Sandy Bridge, you will see that it's flags options. And then depends which program environment is there, it will apply, okay, in case of, yes. First thing to do is program environment. On top of the program environment, whatever you load later, it will depend on the program environment. So Cray, for example, MPI will depend on the program environment. And libc, the math library, will depend on the program environment and so on. So also this option will depend on the program environment. Okay. We are ahead of time, so if there are no questions, the first, I said yes, the practical one is just using, you can use the Cray compiler, and then there are flags that you can use to generate, for example, and you can look at, right? To generate the program library, you will see how it works, which kind of options and so on, and other information that you can get from the compiler, okay? So you can do loop listening, what I mentioned before, -rm, and you can see which kind of optimizations apply to the compiler and so on. And then you can also make comparison between the compilers. So you can compile the same code, you can play, everything is written in the README, okay? You can compile with different compilers, see what are the optimizations, what are the options, so on. Of course, you can open the Makefile, change the flags and so on. You can play with, this is practical one, okay? There are two versions of practical one. One, it is not, it's just sequential, the other one is with parallel execution. Okay.